All right, so we are going to continue learning how to calculate simultaneous equilibria problems, especially ones that involve complex ions and solubility products. So, starting with this problem here, it says using the KSP of zinc hydroxide, and they give it to you, and Kw, calculate the new equilibrium constant for the dissolving of zinc hydroxide in acid. Okay, so let's think about what it is that they gave us first, right? So they gave us the KSP of zinc hydroxide. So we'll start by writing what that equation would look like. Right, KSPs always start with the dissolving process, right? So you have your solid on the left, you got your ions on the right, okay? And just as reference, just write it off to the side. Okay. And they mention Kw, okay? They're mentioning Kw, and the reason why you're going to need that is because I need an equation which represents zinc hydroxide dissolving in acid, meaning acid is a reactant. So if we think about what Kw represents, Kw is H2O dissociating to form H plus OH minus, right? And we know Kw to be 1 times 10 to the negative 14th. All right. So currently, with these two equations, the first thing you want to find is if they have anything in common. What do they have in common? Yeah, the hydroxide, right? But algebraically, nothing can be eliminated yet. But I can manipulate the equations so that the hydroxide does get eliminated by reversing it. So let's rewrite this equation backwards. All right, and remember that when you do so, the equilibrium constant will now, how is it changed? How do I find the equilibrium constant now for the reverse reaction? Inverse of it, right? So this K will be 1 over 1 times 10 to the negative 14, which, of course, is 1 times 10 to the 14. Okay, so that's our new. So I'm going to cross this one out so it doesn't get confusing, so we don't accidentally use it. All right, so looking at what we have, can I combine my two equations to successfully cancel the hydroxide? I can partially cancel the hydroxides, but the equation doesn't mention hydroxide as being present, which means I need to cancel all of the hydroxide. So what do I do? Yeah, let's multiply it. All right, so multiply everything here by 2, 2, 2, 2. And when you do that, the K will have to be, the coefficient that you used, you'll have to square it, which would be 1 times 10 to the 28th. Okay, so we made two alterations to the given equations, right? We reversed it, and then we multiplied it by a coefficient of 2. That factor of 2 that we multiplied by is the exponent of the K, and that's why we end up with 1 times 10 to the 28th. Now can we cancel? We can cancel 2 hydroxides. So the resultant equation will be zinc hydroxide solid plus 2H plus forms zinc ion and 2 waters. And the K for this reaction, because I now have individual equilibrium constants for the equations used, to find the overall K, I have to take the product of them. So I'm going to be multiplying for the original one, 4.5 times 10 to the negative 17, by 1 times 10 to the 28th, which is going to be 4.5 times 10 to the 11th, which is very high. What does that tell you about the likelihood of being able to dissolve zinc hydroxide in acid? Very high, yeah. This reaction is going to happen no problem. Go all the way to the right. Okay, so this is the general, approach to multiple equilibria. Write down the relevant equations. You know that if they're going to be useful to each other, they have to be combined, right? And so you have to algebraically combine them. And just remember the rules for the equilibrium constants. What do you do to manipulate them when you multiply something or when you reverse it? Okay, let's try another one. What is the solubility of silver iodide in 5 molar sodium thiosulfate? And they give us a KSP for silver iodide, and they give us the KF. Right? Remember, KF is the equilibrium constants for complex ion formation. So let's start by writing out the relevant equations. So AGI okay, and that KSP is known. Okay, and they give us the formation constant. So the equilibrium equation for the formation of complex ion is simply the ions combining to form the complex ion. All right. So, can I combine these, or do I need to manipulate these somehow? What do you think? I can go ahead and add them, right? Because what I can reduce, or I can simplify the silvers, right? Subtract silvers from both sides. That's going to tie these two together. So now I have AgI solid with 2 thiosulfate ions forming the complex and the iodide ion. Okay, so multiply the individual K's to get the new. I get K is equal to 0.00435. I guess we'll round it later. Okay, so I have an equation to work from. Let's read the problem a little more carefully now. What is the solubility of silver iodide in 5 molar sodium thiosulfate solution? So if I'm dissolving this in a solution of sodium thiosulfate, what kind of problem is this? Or how do I set it up? Or what do I need to know about this? There's a common ion. And in common ion setups, you have a concentration value in the initial row for one of the ions. Here it is sodium thiosulfate. The sodium is irrelevant because that's not even part of the equilibrium. It's completely soluble, but it's the thiosulfate that we need to account for. So the molarity of the thiosulfate is 5 in the initial column. Oops, actually, nothing goes there. That's a solid. All right, and then from this point on, you carry this out just like you would any standard equilibrium ice table problem. Take a minute, finish it out, see what you get for your solubility. Whoops, that's in the wrong place. All right, did you get the same ice table set up? All right, so pop this in to the solver. We get a solubility of 0.29 molar. You guys get that? Okay, good. So pause and reflect, right? So silver iodide, normally considered insoluble according to your traditional solubility rules. If I tried to dissolve silver iodide in water, very, very little. But we can get a concentration of 0.29 molar if we provide thiosulfate, right? So allow for the formation of a complex. And yeah, the product is silver thiosulfate, which is a complex ion. But what you can do with this higher concentration, this 0.29 molar of the silver thiosulfate complex ion, because it's now dissolved, you can now get rid of you can destroy the complex ion later on, resulting in silver ions being present, right, in solution, and maybe precipitating out if you need to recollect it. Okay. So this was a complex ion problem. This was a multiple equilibria problem, right? Okay. Moving on. What is the concentration of zinc, of tetrahydroxy zinc, if, and now we have measurements, so we got 10 milliliters of 0.2 molar zinc, 10 milliliters of 6 molar sodium hydroxide, and give you the Kf value. That's not a KSV value. That was a typo. It's a Kf value. All right. So, what is the concentration? That's the goal. All right. So, suggestions on how we start this problem now, seeing what you've seen. Start us off, Ron. What should I do first?
Write out the formation equation for zinc. ZnOH4.
Okay. So Zn these charges on these complex ions, guys, they should make sense to you, right? Right, you're just adding them, right? If you have a positive 2 charge in a zinc ion, but you have 4 negative charges you're adding to it, that's why the resultant charge is -2. Okay, and the Kf is known. Okay. So concentration if zinc nitrate is added to hydroxide. Okay. So now what? When they say concentration, it's implied that they mean resultant concentration or equilibrium concentration, right? That's implied. Concentration at equilibrium. So let's start by finishing out our ice table. Okay, what do we know? We know that we had 10 milliliters of this solution and 10 milliliters of another solution, right? So we need to recalculate molarities because those were the concentrations when these were alone in their own bottles. But now that you're going to take a sample of each and put them into a test tube, they both expand into each other. You have to account for the new volume. So let's recalculate our concentration. So recalculate the moles of zinc. This is going to be in a volume of 20 milliliters, so 0.02, right? So 0.1 molar. zinc. And for the sodium hydroxide, we've got 10 milliliters, 6 molar. So 0.06 moles NaOH over 0.02 liters. That's going to be 3 molar. Okay, so I have my initial concentrations. Now, we said we have 3 molar sodium hydroxide, but really, because sodium hydroxide is a strong base, completely soluble, I'm ignoring the Na as it's a spectator. I'm only using that as hydroxide's concentration. So, go ahead and place them into the ice table. And work it like you normally would. I need more room. Let me know what you get. All right. Wait a minute. There's no negative sign here. Sorry, I goofed. That's not a negative. So here's the thing. My calculator is giving me an error, right? This is a polynomial beyond the scope that this calculator wants to deal with. So let's look for simplifications, which we kind of forgot about that. The simplification rule. We could totally simplify this. So of this equilibrium expression, what can we simplify? What do you guys remember about the simplification rule? What's the magnitude of the k, the exponent on the k? 10 to the 17th. What's the magnitude of your initial starting concentrations? Well, 0.1 is 1 times 10 to the minus 1. How many orders apart is the k from your initial concentration? 16. I think that's a big enough difference, right? So that means this. Ignore the subtraction or addition of x within quantities. So this reduces down to this. Go on.
If the k is that large, could you possibly assume that the reaction goes to completion?
Yes. And that's where I was going to go with this. Let's finish the calculation and then discuss. All right, so 4.6 times 10 to the 17th times 0.1 times 3 to the 4th power. All right, so S is 3.7 times 10 to the 18th. What? That's like super duper soluble. What this is telling you is that this equation here, it goes so far to the right that everything on the left side goes as far forward as possible. So let me ask you this then. I mean, is this really even an equilibrium if it goes so far to the right? Yeah, you know, arguably, maybe not. Right? It goes so far to the right, there's almost virtually no backwards reaction. So that means the concentration of your product is essentially the same as what? Whichever one you run out of first, yeah. The limiting reactant, guys. You see that? Do you remember the first lab we did? The determination of the equilibrium constant, how we did 2 trials. How the first one, I had you use 0.2 molar iron, but when you actually tested the equilibrium trials, you used 0.002. Do you remember that? And how I said, you know, oh, we're using this really concentrated one first because it ensures that the concentration of the complex ion is known. Remember that? This is what I'm talking about. If you know the equation goes so far to the right, you can be all but assured that the limiting reactant determines the amount of product that's made. And the equilibrium, it's almost not even an equilibrium at this point. It's just a matter of stoichiometry. But you have to figure this out first. You have to solve for it first. Okay. All right. I think we have one more. One more? No, just kidding. Way more than one more. All right. We'll do this one here. Okay. Think of this, the remaining problems in these notes, think of this as a precursor to the next lab that we're going to do because it's essentially the same philosophy and the same general steps. All right, so what do we have here? I've got 1 milliliter of silver nitrate mixed into 1 milliliter of potassium iodide, and I'm going to add this to 98 milliliters of water. They're giving me the KSP for a silver iodide. Is there a precipitate? Any question that asks, is there precipitate or which way the reaction is going, this is either a P or a Q problem. Right? But because there's a KSP value, meaning a solid, this is a P problem. So you're solving for P, and then you're going to compare it to K. So first thing that might be confusing is notice that your KSP, the compound is AgI, right? So yes, you are mixing 2 solutions, but you need to understand that the nitrate and the potassium are spectators and they are irrelevant. And so you can go ahead and start. Because they gave you a KSP value, you write a KSP equation. Right? That is what you do. You write your equation based on the K that was given. So AgI, solid. Okay. And I need to solve for P. P would be the concentration of Ag initial times the concentration of I minus initial. So I need to find those 2 things to solve for P. So let's solve 0.001 liter times a molarity of 0.001. So this is going to be 1 times 10 to the minus 6 moles of Ag, and over here 0.001 liter times 0.001 molar, same number of moles, right? But they are being mixed, and we need to be mindful of what the total volume is. What is the total volume? 100 milliliters, right? So let's calculate our molarity. So 0.1, divide both by 0.1. And so really your initial concentration of silver then is 1 times 10 to the minus 5th molar. And likewise for the iodide. Or in other words, your P is 1 times 10 to the negative 10th. So compare that to K. That is far greater than the KSP value of 8.5 times 10 to the negative 17th. Too much, P is larger, too much product, this reaction is going to go in reverse. We will see a precipitate form. All right, you guys okay with this problem? Everything makes sense so far? Okay, so continuing on. So now imagine at this point you have a test tube, and you got your solution, and you see the solids, right? Of course, that solid there is AgI. Is this solution saturated? Yes. Yes, it is at equilibrium. If solids form, that is evidence that you are at equilibrium after much shaking. If they're still there, then you are at equilibrium. All right. So, if there is a precipitate, it is centrifuged and decanted. 5 milliliters of the supernatant is mixed with 5 milliliters of water. It is shaken again. Okay, what's the concentration of both ions? All right, so here's what's happening. The solution, the saturated solution that you made, basically we're taking 5 milliliters of it, and we're adding water to it. Does that make sense, guys? We're taking the solution above the solid. That's what the supernatant is. It's the liquid above the solid. And we're just pouring 5 milliliters of it into another test tube, and then we are adding water. So now what we have is a test tube with a total volume of 10 milliliters. Okay. What's the concentration of both of the ions? Rohan, what do you think?
The solution is still saturated, it's in equilibrium, so it should be just the KSP and molar solubility problem.
Right. So we have to solve for S. Right. So let's do that. So, I'm sorry. Wait. Back up. No. It's a little bit. It's not as simple as that, because we have the new volume to account for. The solution was saturated when we put it into the test tube first, but now we've doubled the volume, right? Because we added 5 more waters to what was the saturated solution. So now it's less than saturated. So the concentration is not S. It's effectively half of S. Okay. So what we need to do, we need to find what solubility is first, but once we know what the concentrations are at saturated, we have to take into account what the new volume is and recalculate what the molarity is. So, all right, so AgI. So first step, solve for S. Okay, so KSP 8.5 times 10 to the minus 17th is equal to S squared. S is the concentration, the molar concentration at equilibrium, i.e. the solubility. Okay, so S is 9.2 times 10 to the negative 9th molar. Whoops. Times 10 to the negative 9th molar. Okay, so that's the concentration of a saturated solution. That's the concentration of Ag and I minus S when it's saturated. But we diluted the original saturated solutions. So we have to recalculate what those concentrations are. So, number of ways you can do this, right? So, for example, if this is 9.2 times 10 to the minus 9th molar Ag ion, there was 5 milliliters of it So we can find out how many moles there are and then redivide by the new volume. Does that make sense, guys? Rohan?
So isn't the solution like shaken and centrifuged again and decanted after the addition of water? So we reach equilibrium again?
Shoot. Yes. I didn't read that second sentence. Okay. Wait. Let me think. Shaken again, centrifuged again, decanted again. Okay. Okay. So in other words, we're not done yet. All right. So here's what happened. So we took the solution, we added water to it, and now we have the concentration of both ions. What we need to do is we need to determine if this will precipitate again, right? So we need to take these concentrations. So 4.6 times 10 to the 9th molar silver, and that's the concentration of both, right? Does that, you guys okay with that? Because it's a 1-1 ratio. We did the exact same thing. So let's solve for P and see what happens with these values. So the value P is 2.1 times 10 to the negative 17. Your K is 8.5 times 10 to the negative 17. So actually, in this case, P is lower than K. So we are not going to get a solid, so that we actually can't decant it because nothing precipitated. So in the end, these are the concentrations because it never precipitated again. Okay. All right. So no need to centrifuge or decant because nothing precipitated. All right, so we have the concentration of both ions now in part B. Let's move on to part C. 5 milliliters of that newly decanted solution. Well, it's not decanted. We're just taking 5 milliliters of that solution. Okay, is mixed with some sodium chloride and water. Is there a precipitate? So sodium chloride. So now what we're doing is we're evaluating the equilibrium system for silver chloride. So they gave us the KSP. Whenever in doubt, guys, and you're trying to figure out what equation to write, look at the KSP value they gave you. That's the equation you write. So the KSP for silver chloride, so it's Ag plus, Cl minus. Okay, all right. I need to refigure out what the concentrations are because I need to know the concentration of silver ion and I need to know the concentration of chloride ion. So the concentration of silver, because we sampled that solution and we took 5 milliliters of it, so we need to figure out what the concentration of silver is. So for the silver concentration, we took 4.6 times 10 to the minus 9 molar solution, and there was 5 milliliters of it. So we need to figure out how many moles of silver there are. Okay, and the total volume, because I'm adding 1 milliliter and then 4, the total volume is going to be 10. Okay, so that's my initial concentration of silver. I need to do the same to figure out the concentration of chloride. So what do I know about chlorine? there was 1 milliliter of it. And the molarity of it was 0.001. So this is 1 times 10 to the minus 6 moles of chloride divided by 10 milliliters. So 1 times 10 to the minus 4 molar chloride. And so now I can solve for P and make a decision. And that's a funny, I don't like the way that looks. That's a 4. It didn't look like a 4. There we go. And I don't know why I used the calculator for that. All right, P is 2.3 10 to the negative 13. The KSP for silver chloride is 1.8 times 10 to the negative 10. Do we see a precipitate?
No.
We do not. P is less than KSP, which means at equilibrium, or it means we do not have enough product. This reaction will move forward. If it moves forward, it moves away from the precipitate, so we don't see any solids. All right, I'm going to pause here for a second. Do you guys see the theme of what these problems have been doing? We carried out a reaction in one test tube. We took a liquid, we transferred it to a second test tube. And what's vital in that process is knowing what the concentration was before in the first test tube. And then you recalculated what the concentration was in the second test tube. And then you do something else to the second test tube, right? It's very, very important to keep track of what the concentrations are. The tricky part is figuring out how you're going to calculate the concentration in each tube every time you make a change. Right? So these problems are the kind of things that, you do once and then you do it over from scratch and check yourself again, make sure that everything made sense. Okay, last leg of this problem, and we'll probably stop there. All right, so 1 milliliter of 1 molar sodium chromate is then added to that test tube. Which test tube? This test tube. And they give us a KSP. Is there a precipitate? All right, so it's now silver chromate that we're paying attention to. So Ag2CrO4, 2 Ags plus chromate. Okay, so we need the concentrations of silver and chromate now. So, do we know the concentration of silver from the part C? Yeah, we do. So we need to realize that we took, we need to realize that we are now adding 1 more milliliter of volume, so we need to recalculate what that molarity of silver is. So, let's change colors just for the sake of it. Okay, so is that not dark enough? Here, I'll go some darker. Okay, for silver, let's take the molarity of silver, 2.3 times 10 to the negative 9, and there were, oh, wait a minute, silly. Wait, guys, we don't need to I already know the moles of silver, because the moles didn't change, right? It was 2.3, remember that? 2.3 times 10 to the negative 11 moles of silver. We're just dividing it by a different number. We're now dividing it by 11 milliliters. That makes sense, guys? You see where I'm getting this number from? Earlier, when we calculated the moles of silver up here, and we redivided by 10 milliliters to get the concentration, the amount of silver is still the same, so it's the same number of moles. The only difference is we're dividing it now by 11 milliliters. So, 1 times 10 to the minus 9 molar silver. Okay. And now let's calculate what our chromate is. So we had 1 milliliter of 1 molar. Okay, so it's 0.001 moles chromate. And this is a total volume of 11 milliliters. .091 molar. All right, and we'll plug them in for P. All right, the value for P, 4.0 times 10 to the negative 19th. How does that compare to the KSP? A lot smaller. Yeah, nothing's going to happen. There's no precipitate. This reaction is going to go forward. Okay. All right, so that's enough of that for now.